Hi, I'm Rich with Inside HPC. We're here at the GTC 2012 conference. I'm here with Rob Farber, author, consultant, formerly of the labs, a guy who knows a lot about GPUs. So Rob, one of the features we did not cover yet at Inside HPC is SMX. And I was wondering if you could kind of lay that out for me. How does it work?
So it's the SMX processors. Those are the streaming multiprocessors that NVIDIA puts on the GPUs. And they're wonderful things because the GPU architect can print as many of them as he wants to get a particular performance for a particular price and thermal envelope. Okay, so heat, price, and performance. So what they did with Kepler is they added some extra smarts to the streaming multiprocessor, which is the SMX, for an improved version. So part of that has to do with the scheduling, but one of the really cool things is that they've added something called superscalar, a kind of a superscalar kind of behavior. So the whole idea behind GPUs is that you throw a whole bunch of threads at the hardware, and the on-chip scheduler on each SM can detect when all the data dependencies are resolved. And so what happens then is that execution then can start executing. So it's like playing poker. If I have a whole bunch of threads, chances are really good that something's going to be ready to run at any time, and you're going to get very high performance, high throughput. So what they did with the scheduler on the SMX streaming multiprocessor is they added the intelligence to look ahead an instruction behind the next instruction that's coming up, see if there's no dependency, then they can flatten it out. So you increase your bets, you increase the number of instructions that can potentially run at any time, which allows them to make better use of the arithmetic units inside the streaming multiprocessor, and to get much higher utilization. So the nice thing is that with this additional intelligence, then they can keep printing these and get very high throughput with, again, massive numbers of threads, which is one of the whole ideas behind GPU computing and behind CUDA, is that you can scale to use those thousands, 3,000s of threads concurrently without having to do massive changes to your code.
Nice, nice. Rob, we were talking earlier about some of the secret sauce, some of the lesser known performance features in Kepler, and why don't we start there? What are some of the things you learned in this week about Kepler?
Well, what I'm very excited about is the ability for kernels to generate work themselves. In my book and in my tutorials, I teach that there's 3 rules for high-performance GPU computing. The first is get the data on the GPU and keep it there, because you have that PCI bottleneck, the straw. Now, I'm very excited about the Gen 3 support in Kepler and in the newer NVIDIA products, because that's going to almost double the bandwidth, is my understanding. So that's going to really widen that little data pathway onto the GPU.
So if you do need to move data back and forth, you've got a wider pipeline, but
Yeah.
The objective is to stay on that GPU if you can.
The objective is to have the data on the GPU. The reason why I'm kind of waffling a little bit is because they have these wonderful asynchronous communications capabilities. So I can be transferring data onto the GPU, transferring data off the GPU, and computing at the same time. So there's some wonderful examples of that. For example, the FeeGem code that 2 friends of mine, Yvonne Girato and Filippo Spiga, created, showing how to do this for matrix multiply. It's freely downloadable on the web. And it's a great example for people to go in and take a look how to get very high performance with 2, 4, 8, 16 GPUs, where you're doing all sorts of these transfers. So the beauty of partially is with the PCI Gen 3 is a nice addition, but that also gets back to the first rule of get the data on the GPU and have it ready there to compute with, okay? The second one is, well, gee, you've got this teraflop, multi-teraflop capable hardware platform, and you have to give it enough work to do. So the host says, well, do this bit of work. Well, if you give it 500,000 operations to work on, it's going to finish it like that, and there's just not enough time to start the next kernel. So if you only use 50% of those cycles in your kernel before getting to the next kernel, you lose 50% of your performance, or 70%, or 90%. So the nice thing is that I can keep the program execution on the GPU. So I can sort of chain from one kernel to initiate another kernel and keep going. So I'm keeping the computation on the GPU, just like kind of a variant of that first rule I talked about. But more than that is it's much easier to give the GPU enough work to do And even more exciting, which is getting everybody who does anything with variable size meshes and variable size problems, is that you've got conditional capabilities so that you can work with adaptive meshes and other computational data structures to be very, very efficient. And that's actually one of the big points of the keynote demo of the galaxy collision, not the fact that we're all going to collide with the Orion Nebula in 3 billion years. But what's cool for me now and for my CUDA developers who talk to me and want to learn how to use this capability is that you can break up the problem so that you can effectively model that. My understanding is they tried for a year to get that simulation running very efficiently on Tesla, and in a short time, a weekend or within a week, using these new Kepler features, they were able to get that working very, very fast. So that's rule 2, is give the GPU enough work to do. Pardon me. The last one is to make use of the ON-SM plus SMX computing units that we've been talking about, so that you avoid global memory bandwidth bottlenecks. So if you think about it, the 100+ gigabytes per second that global memory can deliver, that sounds like a big number. It's wonderful. It's kind of like having the jets flying over. It's just you blast data through super, super fast.
Yeah.
But the challenge is that you've got that teraflop supercomputer saying, feed me, feed me, feed me. So if you do the numbers, 150, 160 gigabytes per second is just not sufficient. So they're also increasing the memory bandwidth capability, which is very nice. Meanwhile, they're also making things much faster with atomic operations and things like that to make the programmer's life easier, although I don't necessarily advocate using atomic operations unless you absolutely have to, because if you remember that we've got that scaling to thousands and 3,000 threads, well, atomic operations have the potential to impose a bottleneck on that, so you don't get that scaling. So when you get the new next generation GPU that runs with 5,000 or 10,000 threads, it may not run quite as fast as you want. Stick with pure CUDA and don't use atomics unless you need to, but it's a good thing that NVIDIA is optimizing.
Yeah. So Rob, some of this stuff sounds really difficult. Is this grad level stuff strictly, or is there a happy ending to that?
There's a real happy ending, and hopefully I didn't lose the audience during that whole spiel.
No.
And but actually, what makes me feel really, really happy is that there was a presentation by a professor at Cal Poly who is teaching CUDA to undergraduates. They have a little bit of basic C programming, a little bit of C++ programming, and it's very effective. He wrote a paper in the journal, you have to forgive me, I forgot the name, but it's the journal for professors to publish their results on teaching methods and effective techniques. But undergraduates get this, and they're able to transition immediately from C++ to using CUDA and programming with massive numbers of threads, tens of thousands of threads. It's not graduate level stuff, he's doing it with undergraduates. More than that, they're able to do really fun stuff in addition to programming with just with CUDA. They're able to mix that with rendering, so it becomes interactive and they're able to play with it and they're actually able to see the results of their work very effectively. So that validates my approach in my book, CUDA Application Design and Development. I'm just so very excited because I took that approach. Right off the beginning, you look at your first C++ program. The next one is basically your programming in CUDA. And right after that, I show you how to effectively solve real problems, optimization problems. Very effectively, I take you through and show you how, in chapter 10 of the book, how to scale that to 500 GPUs for exascale capability and beyond. More than that, with the real-time video processing example, you can plug in a webcam or have the professor give their students a movie file, and you can do different things like sole edge detection. You can make a Kinect type of video controller to fly through the 3D virtual world that you create with the Perlin noise generator, and it's a way of getting students engaged. We were the #1 selling book, CUDA book, at the Morgan Kaufman booth at Supercomputing. I'm happy to hear that we're the #1 selling CUDA book at GTC this year, so I'm very excited, and with that validation, we have CUDA now being taught at over 500 institutions around the world. My book has gone into translation within the first month of being in print. It went into its Chinese translation. We're working with professors in India, Europe, all around the world. It's just a fantastic experience. It's absolutely wonderful.
Oh, well, and then I have to ask, is there a sequel or something coming up?
Oh, obviously, yes.
You're outlining something now, or what are you
yeah, I am. So what we've been hearing about is a lot of buzz about something called OpenACC.
Yes.
So a lot of programmers have been hearing about, know how to use OpenMP to parallelize for loops. And OpenACC broadens that out to work with coprocessors, GPUs, and it will work also on other devices as well, such as mic, AMD GPUs. So I see a tsunami of compiler innovation coming down in the next year, which I'm really excited about. So the Portland group, PGI, they've already got their CUDA x86. They're working on OpenACC, as well as CAPS Enterprise. The Pascal guys are doing some wonderful work with getting in and trying to get the absolute best performance. And the NVIDIA NVCC compiler team is doing wonderful things. So opening up the API to use the what's called the LLVM. I'm sure that we're going to see CUDA ARM, that we will see CUDA x86 and CUDA other types of projects coming down the line as open source developers start working with this open API. There's a lot of room in that ecosystem for the compiler guys to optimize the parallel sections of code so that they can have their value add, so they can promote, you want to buy my compiler. So NVIDIA, I think, played this card right because they've opened it up to make it a competitive marketplace so that people write good software to sell more of their chips. I really think that that's a good business model for them. It seems to be working well. And surprisingly, being the developer outreach kind of guy that I am, because I want to get this technology into the hands of corporations and students, is that I've heard that people have actually been able to take the R statistical language, just a program, and just compile that and run it on the GPU. So this is a new project, kind of like the Copperhead Python project, and it just set me back when I heard that, is that the potential for the advances that are coming in the compiler technology. We will see, looking at my crystal ball. I'm not rich on the stock market, so you have to have to take your value, your sage at face value. But there's just so much potential for innovation and so much capability to make this simpler, that returning back to the sequel for the book, I want to incorporate that, make your life simple, use the simplest possible API, program with that. When you need to, delve down into CUDA, make use of the Kepler features that are specific to your application. And that's one of my value adds, is I can show you how to go from that simple model to basically how to get everything out of the processors that you want. And in fact, there's actually some nice roadmaps for moving forward for bringing this into the enterprise that I'm very excited about.